Hey everybody, Trey here, and welcome to episode 2 in this module on satellite foundations. In our last episode, we talked about the basics of how satellites work, and in this episode, we're going to go over the specific satellite bands that are most important for severe weather forecasting and nowcasting and storm chasing. Just a couple notes before we get started. I'm not going to go through all the 16 satellite bands in this episode, only the ones that are most important for severe weather forecasting and storm chasing. And for this episode, I'll be using the College of DuPage satellite and radar page for all of the satellite data in this video, but all of the bands will be available through really any source of satellite data that you choose. So without further ado, let's go ahead and get started. The first important band for storm chasing is band 2, which is the visible band. If you were an astronaut on the International Space Station looking down at Earth, what you would see with your eyes is basically what visible satellite imagery is. Now, there are actually two different bands of visible imagery. Band 1, which is the visible blue band, has a wavelength of 0.47 micrometers, which is located in the blue portion of the visible portion of the electromagnetic spectrum, hence the name visible blue. Band 2, which is the visible red band, has a 0.64 micrometer wavelength, which is located in the red portion of the spectrum. Whenever you're doing any kind of severe weather analysis, you want to be using band 2, which is the visible red band. Band 1 is good for looking for aerosols, smoke, etc., but clouds don't come through as robustly, as sharply as they do on band 2. Band 1 has a slightly lower resolution than band 2. At the point directly below the satellite, band 1 has a resolution of 1 kilometer, while band 2 has a resolution of half a kilometer. You're going to get slightly sharper imagery with band 2 than you are with band 1. Band 2 has the finest resolution of any of the 16 satellite bands, so it's excellent for severe weather analysis. And what you want to use visible imagery for is to locate clouds. You can look at where clouds are, how they're organized, what their movement is, and other behaviors. And because the resolution is so fine, we can see very small scale features that other bands just can't. For example, we can see things like overshooting tops, outflow boundaries, etc. Don't worry, we're going to dive into each of these features starting in the next episode. This episode is just meant to get you familiar with the most important bands for storm chasing, and then we'll go forward and look at what you can actually use these bands for when you're out in the field. So again, visible satellite imagery is best for identifying the locations of clouds and assessing their behavior. We can also differentiate the different altitudes of clouds in a visible satellite image, high level versus low level, and the different types of clouds in a satellite image, cirrus versus cumulus versus stratus, etc. In this example, you can see the expansive layer of clouds on the right side of the screen. These are stratus clouds. Stratus clouds occur in layers. The clouds are usually pretty homogeneous within that entire layer, not much change over the entire layer. And stratus clouds are low-level clouds. In contrast, you see these wispy clouds coming in from the west. These are cirrus clouds. And cirrus clouds get their wispy appearance because they are made up of ice crystals. Because they reside at the highest levels of the atmosphere, so cirrus clouds are high-level clouds. Even further evidence that we can determine the altitudes of clouds using visible satellite imagery, you can see the cirrus clouds overspreading over the top of those lower level clouds, so cirrus clouds, high level clouds going over the top of low level clouds. And then you see these puffy clouds at the bottom left of the image. Those are cumulus clouds. Cumulus clouds have that cauliflowery, puffy type appearance. And when those cumulus clouds, which are low level clouds, grow within an unstable environment, they can become cumulonimbus clouds or thunderheads. Of course, we're going to talk a lot more about the features of cumulonimbus clouds and what they mean for thunderstorm intensity starting in the next episode. But you can see all the different types of clouds that we can identify on a visible satellite image.
Hey everyone, the video you're watching right now is a preview of the content that's available inside of the Chaser Academy. The Chaser Academy is our subscription product where we teach people of all skill levels how to chase storms smarter and more successfully. You'll definitely want to check it out at the link in the description below. And if you're not ready to purchase anything, that's okay too. We've got a host of free resources down in the description as well. Thank you for your time, and now back to the video.
Now, when the sun goes down in your area of interest, when it's dark out, visible satellite imagery is rendered useless. Just like if you were to turn the lights out in a room you can't see anymore, same thing with visible satellite imagery. So you cannot use visible satellite imagery at night, only during the day. The next important type of satellite imagery for severe weather analysis is long-wave infrared imagery. Long-wave imagery measures a quantity called brightness temperature, which is the measure of the intensity of electromagnetic energy coming from a source. In simple terms, long-wave imagery estimates the temperatures of the tops of the clouds. From that, we can use long-wave imagery to assess the intensity of storms. More intense storms tend to go higher up into the atmosphere. They tend to be taller. Taller storms have colder cloud tops. Therefore, the more intense the storm is, the colder its cloud tops are likely to be. Now, there are two different bands of long-wave infrared imagery that you can use. Band 14, which is the standard long-wave infrared band, or band 13, which is called the clean long-wave infrared band. Band 14, which has a wavelength of 11.2 micrometers, is slightly more susceptible to absorption from water vapor than band 13, which has a wavelength of 10.3 micrometers. This means that the brightness temperatures measured by band 14 are going to be slightly too cool than what they should be, and slightly cooler than those of band 13. Hence why band 13 is called the clean band. Still, these two bands are basically interchangeable. They're showing you the exact same thing, long-wave infrared imagery and brightness temperatures, but you might see some slight differences in the images between the two bands, and the brightness temperatures shown in band 14 might be slightly cooler than what they should be overall, but it's still a perfectly viable band to use for assessing the intensity of storms. In these long-wave images, your warmer colors correspond to colder cloud top temperatures. So your oranges, reds, and blacks correspond to colder cloud top temperatures indicative of more robust storms, whereas your cooler colors, your purples, blues, and greens, those are indicative of warmer cloud top temperatures and therefore less robust storms. And unlike visible satellite imagery, long-wave imagery can be used 24/7, day or night, because it's measuring temperatures. So it's a good substitute to use at night when visible imagery is rendered useless. The final type of imagery that's important for severe weather forecasting and storm chasing is water vapor satellite imagery. This is comprised of band 8, which is upper-level water vapor, band 9, which is mid-level water vapor, and band 10, which is lower-level water vapor. Technically, these are still infrared bands, so they're sensing brightness temperature, but water vapor absorbs radiation very well at the wavelengths of each of these bands, so you are able to get a good representation of where there is high and low water vapor or moisture content in the atmosphere. You're going to see lower or colder temperature outputs where water vapor content is high in the atmosphere, and you're going to see warmer or higher temperature output when there is lower water vapor content in the atmosphere, i.e. where it's drier. Each successive water vapor band can see a little bit farther into the atmosphere. Band 8, which is the upper level water vapor band, can see down to about 200 to 300 millibars, which is about 30 to 35,000 feet or so into the atmosphere. This is where the jet stream resides. Band 9, which is the mid-level water vapor band, can see down to about 500 millibars, which is about 18,000 feet in the atmosphere, and it's where we look for troughs and ridges. Troughs are associated with low pressure, ridges associated with high pressure. Troughs are usually a key ingredient in severe weather. And band 10, which is the lower level water vapor band, can see down to about 750 millibars, which is the lower middle portion of the atmosphere. Now there is one caveat. If there's a dense layer of clouds aloft, that's going to obstruct any moisture features that are occurring at lower altitudes. So if you have a thick band of clouds at, let's say, 30,000 feet, well, those mid-level and lower-level bands are going to struggle a little bit to decipher any notable moisture features because of that thick band of clouds in the upper levels of the atmosphere. We've already been hinting at it, but one of the main uses of water vapor imagery is to assess atmospheric moisture content. The whites and greens, and even the milky blues you see here, those are indicative of colder brightness temperatures and therefore higher moisture content. While your darker blues and your yellows, those are indicative of warmer brightness temperatures and less moisture content. You'll often see the yellows and even some oranges more so on the mid-level and the lower level water vapor imagery. The oranges indicate very dry air in the lower portions of the atmosphere. Another good use of water vapor imagery is to identify troughs and ridges. Just as a quick refresher, troughs are those downward kinks in the geopotential height contours, the solid black lines on your upper air maps. Troughs are often associated with low pressure at the surface and rising motion in their exit region, the area to the right of the axis of the trough. So troughs have a lot of the ingredients that we need for severe storm formation. Now, you can mainly pick out troughs from your upper air maps, but sometimes they can be quite subtle. Sometimes there are things called shortwave troughs, which are very small scale troughs embedded within a larger trough or just embedded within a belt of zonal or west to east flow. And these can be little extra foci for severe storm development. Sometimes they can be very subtle and they might be difficult to see on upper air maps, but because water vapor is such a good tracer of the mid and upper level winds, we can identify shortwave troughs perhaps a little bit better sometimes by using water vapor satellite imagery, particularly the upper level or the mid-level water vapor bands, band 8 or band 9. So using band 8 here, let's look at this example. So you can see the movement in the milky white and green areas, which of course are your areas of higher moisture content. Those are going to be indicative of troughs and ridges. So we can see one up here in the northern US into southern Canada. You see the counterclockwise rotation of that kind of milky white area and that little band of darker colors there, indicative of drier air. That is a trough. So we can identify that there's a trough right there in the northern plains, upper Midwest into southern Canada. We can also see this big swirl out here over the Atlantic, big counterclockwise swirl there, likely a large trough out here as well. Now, looking here in the southeast, you see the greens here, which are indicative of thunderstorm activity. Those are kind of spinning in a clockwise direction, which is indicative of a high pressure ridge that is in place across the southeast. Same thing here in the western US. You see the milky whites here kind of spinning in a subtly clockwise manner. That can tell us that there is also a ridge here across the desert southwest. Now, one thing here to note is to the south of this ridge. Notice this little swirl, little band of darker colors here, and you can see a little bit of subtle counterclockwise curvature in the milky whites there. So that is a little bit of a shortwave trough that is located there just to the south of the southwest ridge. And so let's see how we've done. So I'm going to mark our troughs and ridges here. So here is a trough out here in the Atlantic. I'll mark these as L for low pressure areas. Then we have a ridge of high pressure out here across the southeast into the Gulf, high pressure ridge out here across the western US, and a little bit of a trough down here, maybe just on the southern side of the ridge, could be a little bit of a trough kind of pushing into the ridge here. So that might look more like this. Just a little bit of a trough there. That could be what we call an inverted trough, which is an area that is like a trough. There's counterclockwise spin, but the winds are going from east to west instead of what is typical in a normal trough from west to east. So I'll mark that as a little bit of a trough right there on the southern side of the ridge. So let's go ahead and put on our 500 millibar winds and height contours here and see how we've done. So I'm going to pause it. And you can see that we've done pretty well here. The trough here across the northern plains, you can see those height contours there, pretty well-defined trough in those red lines there. Those are your geopotential height contours that will indicate the trough. So definitely a clear trough there across the northern U.S. into southern Canada. We see the counterclockwise flow out here. The lines get cut off in the Atlantic here, but you can see that there is a nice counterclockwise flow around that big swirl in the Atlantic. So we've identified that trough there. A little bit of a ridge of high pressure as well, upward kink in the height contours there, with clockwise flow around it across the eastern kind of southeastern quadrant of the U.S., and then a big ridge of high pressure here over the western U.S. You see the clockwise flow as well, with the closed height contour there over California into Arizona and Nevada. So big ridge there. And we do see a little bit of a disturbance there where we had marked it, a little bit of what we call an inverted trough on the southern side of the ridge. You see the height contour there. I'll take the R labels off, and you can see a little bit of that. So you can see there's still some counterclockwise spin there, even though it is within the ridge of high pressure. So it's basically a trough that's been flipped upside down, and that does also act as a trough would act, just the winds are going from east to west instead of west to east. So that shows you that you can use water vapor imagery to identify the trough ridge pattern pretty well. And for example, this one here, this is pretty subtle. I'll go to our 500 millibar map on the SPC mesoanalysis page. If you were to look at just this map here, you might miss this little trough, this inverted trough out here on the south side of that western U.S. ridge. If you were to just take a quick look at this, you might not even see that. You can see a little bit of a kink there, an upward kink in the winds there, but it's very difficult to see. But you can see how the water vapor imagery makes it pretty easy to see in that very well-defined swirl there to the south of that western U.S. ridge. So water vapor imagery is a very good tool when you are making a forecast, usually the morning of your severe weather event. It's a good way to kind of show you where the trough ridge pattern is, and if the 500 millibar or the 700 millibar map doesn't really show a lot of shortwaves, but you think there might be some shortwaves in the flow, water vapor imagery is a good tool to use to kind of check your work and see if there are any shortwaves, because water vapor, again, is a very good tracer of the winds aloft and can help identify those shortwaves and make them much clearer than they would be than just using an upper air map. So that's going to wrap things up for this episode. There are a number of different satellite bands you can use, 16 to be exact, and hopefully this video gave you some insight into just which of those bands are most important for severe weather forecasting and storm chasing. In our next episode, we're going to start taking a look at some severe weather applications, namely some satellite features and signatures that you might often see before, during, and after storm initiation. So with that, thanks for watching, and we'll see you in the next video.